Hello everyone, this is XM Physics. If we have a battery with negligible internal resistance, then the smaller the external resistance, the larger the power output. This is very straightforward because P is equals to VI. When there's no internal resistance, then the voltage across the external resistance is always the EMF of the battery, and the current through it is simply E divided by R. So the smaller the external resistance, the larger the current, and therefore the larger the power output. In fact, as the external resistance gets smaller and smaller, the power can approach infinitely large. If the battery comes with an internal resistance, then it's a completely different story. With the internal resistance, the voltage across the external resistance is not the EMF. It's only a fraction of the EMF. And by the potential divider principle, we can write it as R divided by the total resistance of the EMF. Likewise, the current flowing through the circuit is no longer E divided by big R. It's now E divided by R plus small r. So you can write this expression as this, and then you plot out the graph, and this is how the power output varies with the external resistance. But this is all math, right? So let's do a bit of physics. Okay, let's see what happens if we use a very, very small external resistance, like zero, like 0 ohms. So when that happens, the current through the circuit approaches the maximum possible current, which is the EMF divided by the internal resistance of the battery. Now that's good, right? A large current is good. But if the external resistance is 0, the voltage across it is going to be 0 because you grab by the potential divider principle. Now you grab nothing. Now you grab a 0 share of the EMF. So if the PD across the external resistance is 0, then of course the power output is 0. So this explains why the power output is very low when the external resistance is too low. Okay, how about we try an infinitely large external resistance? Let's make this infinitely large. Now when you do that, the PD across the external resistance is going to be the maximum possible. That's the EMF of the battery. Now that's good, right? But if you have an infinite resistance here, then the current through the circuit is going to be 0. With 0 current, the power is going to be 0 again. So this explains why the graph goes this way. As the resistance becomes larger and larger, the power actually approaches 0. So too small an external resistance, you get 0 power output. Too large external resistance, again you get 0 power output. So what is that special resistance value, the just nice external resistance, such that you will get this battery to deliver the maximum possible power to the external circuit? So by differentiating this function or otherwise, it turns out that the special resistance value is when R is equals to R. So when the external resistance matches the internal resistance of the battery, that's when you can get the maximum amount of power dissipated in the external circuit. This comes at a price of 50% efficiency, but if you want to maximize the power output, that's the price you have to pay. Alright, that's all. Ta-ta!